We first learned about the Arrhenius definitions for acids and bases, and remember they were limited because they had to be in water. So the second definition, the Bronsted-Lowry definitions, allows a more generalized definition of acids and bases. Now, it does not eliminate the acids and bases that we were talking about before. These definitions include those of the Arrhenius definition. It's just that we don't have to be in water. So in Bronsted-Lowry, an acid is a proton donor. Okay, so for example, let's look at a hydrochloric acid, which we had before when we did the Arrhenius definition. So we have hydrochloric acid, and when we place it in water, what did I say that it did? It has this hydrogen, or H plus is what we're really looking at, which is the proton, and it is donated or given to the water. So hydrochloric acid is still considered an acid because it gives its proton to the water. So in this definition, we're not looking that it has water, or that it forms hydronium ion, which is the Arrhenius definition. We're looking right here where the H plus, the proton, is donated to the water. So it's that act of the acid donating its H plus. So for a Bronsted-Lowry, something to even be considered a Bronsted-Lowry acid, it must have a hydrogen. And so again, we're going to look, acids are going to have, the hydrogen will generally be written in the front of the formula, like HCl, or after the COO and then the H, the carboxylic acid, which we had similar to what we did before. In fact, I had set this up earlier, but let me erase this and let's write the carboxylic acid like I had before. So we have the CH3COOH, and it's this H right here. If I were to draw, whoops, I was going to try to erase. If I were to draw this like the formula really is, the Lewis structure, it's this H right here. And so remember, this definition says we have to donate that proton. So we donate it, and we get CH3C. It would still have this part, because all it's doing in acid and bases is moving that H plus, the proton. So we would still have that part, and then it has this. So again, the carboxylic acid remains an acid because, in this definition, it donated the H plus. And that's the Bronsted-Lowry definitions. So the Bronsted-Lowry, again, just to remind you, it has to contain that hydrogen atom. And for acids, the ones that can be donated in the terms of the formula will either be written in the front, like this is written in the front of the formula, or at the end after, it has to be after this COO. And recall in your homework and things, it may also look, it would be attached to something else, but it may also be written that way because it's a little easier to type. So you can see both examples in your textbook. So it has to contain a hydrogen. Now sometimes acids may have a charge on them. They can be positive, neutral, or have a negative charge. So we're not worried about the charge. We're really looking for that hydrogen. Now the second definition, or the definition of a base, and I'll rewrite it on this one, is the base is a proton, which is an H plus donor. And ask me in class if you're like, how are you saying proton is an H plus? Ask me in class and we'll talk about why H plus is called a proton. But so a base is a proton donor. Now, in order to be a proton, you're probably saying that's the same definition as an acid. Sorry. The base is the proton acceptor. So the acid is going to donate and the base is going to accept. And in order to be a proton acceptor, you must have, the substance must have a lone pair on it. Now, a lone pair of electrons, remember, is simply electrons that are on an atom that are not used in the bonding. Now, normally, when we'll see on the next video that acids and bases will be in the same formula, and so we won't always have to be thinking directly about this lone pair, but I wanted you to understand in relation what's happening. So remember the example of ammonia. And ammonia, if I wrote its Lewis structure, it looks like this. And when we put it in water, the hydrogen from the water, the proton, went on to the ammonia. And that H plus had to contain that electrons for that proton to bond to. So then that was how the hydrogen gets bonded to it. So we got this. So you see, in this case, the proton is being accepted by the ammonia, and it's able to do that because of a lone pair. Now, the hydroxide ion also has lone pairs. If we were to draw it, it has a bond that has 3 lone pairs on here. And so we also see hydroxide ion has lone pairs. So it must have lone pairs to be a Bronsted-Lowry base. So let's look at a reaction and see what happens when we have how we look at these two things. So let's say we have HCl and ammonia together. And HCl and ammonia, if we looked at their reaction, and you do not have to predict what would happen here, this would be given to you. So let's say we have this reaction, and if we're comparing the reactants and the products here, what we notice is that this chlorine over here, the chloride ion, the hydrogen, the proton, has left the chloride, the hydrogen chloride, and gone to the ammonia. Right? So HCl donated the H plus. You could think of it as losing it if you wanted to. And then at the same time, NH3 is accepting it. So if we think about our definitions, in this reaction, HCl is acting like a Bronsted-Lowry acid because it is donating, and the ammonia is accepting or gaining it, and it's acting like a Bronsted-Lowry base. And I can't draw an arrow to the definition because it accepts it. So when we start thinking about Bronsted-Lowry acids and bases, what we notice is the H plus is being transferred between the two different substances. So if you want to investigate more, and then the next video in the reaction of Bronsted-Lowry acids and bases, we'll talk more about how the hydrogen, the proton, I should be more specific, is transferred. And that's what's the result of an acid-base reaction.